Welcome to Q&A Wire.
We have another cogeneration plant to look at. We have steam generated in a boiler. It goes up to 10 megapascals, and we have a temperature going into the boiler of 450 degrees C. We have a mass flow rate into the turbine of 5 kilograms per second. So basically, it says that we have two different operation modes in this. In normal operation, steam is expanded in a turbine at a pressure in a turbine to a pressure of half a megapascal, and then some of it is bled off. So that's routed to this process heater here. So again, we have heat coming, power going in here, into this pump, out of the boiler, or out of the process heater, and out of the turbine, and then out of the condenser also. So we have some coming in. So in normal operation, let's see here. They said, and is right where it is supplied. Steam leaves the process heater as a saturated liquid. So here, and is pumped to the boiler pressure. In this mode of operation, no steam passes through the condenser, which operates at 20 kilopascals. So basically, in this mode of operation, so I have these lines here in blue. That's the second mode of operation. So the first mode of operation, we don't have any of it. Basically, we have no flow here, and then we have really no mixing here. We just go directly into there. So these blue lines are the second mode where we actually need to dump some extra heat that I guess we didn't need for the process heater. So if we don't need all the heat here, we then pump some of it, let some of it go through finish its way through the turbine. And so in that case, we'll get more power out here, but we'll get less heat here. So it's a trade-off, and we'll see that. So again, we can, we know everything at 1. So if 1 was being utilized, we'd find that the power being put into this pump, if it were actually running, would be, and so in the second mode of operation, we have 60% of the steam coming off here instead of 100%. So if this pump were running, it would be 40% of the steam by volume, by mass anyway, which would be liquid at this point, will be going through this pump, and we'll get a specific work of 10.15 kilojoules per kilogram, because we know the pressure at 2 is basically pumped up to this pressure here that it would bled off the turbine. So we know this pressure here is 500 kilopascals, and we know this pressure, and we know the specific volume. So then we know the enthalpy at 2, should there be stuff flowing through there. At 3, again, we have saturated liquid. So we have the pressure and the saturation, that the quality factor is 0, so we can get the enthalpy and the specific volume, and then we can find the work, the specific work being put into pump 2. Now, again, whether depends on how the mass flow rates will be different. In one case, the mass flow rate here will be 0, and here will be 100%, this whole value here. And in the other case, we'll have 60% here, or 60% here, which is what, 3, and then we'll have 2 kilograms per second flowing through here. So there's just two cases. So for each case, the specific work is the same, but the mass flow rate is different. The mixing chamber here, we have, again, we can assume that we have some mass flow rates through all of these. We can later set some to 0. So we have the entropy flow out equals the entropy flow in, and we know all of these things. So we can figure out what H5 is. So we can figure that out because, let's see here, in the mixing chamber, we're going to, in this case, if we have mixing here, so we're assuming here now that we have some flow there, so that we're utilizing the flow coming in from here, and in one case, so H5 is, this would be, let's call this H5 prime, not prime. let's call it H5B instead of, give it some other notation, because this is the enthalpy at 5 should we be running in this mode where we go through the condenser. Now, if we don't, then we're just coming straight through here, and the enthalpy at 5 is the enthalpy at 4. So again, you can call this one H5A for part A and part B of the problem. Now, let's see here. We have everything's isentropic, so we've used that fact here. And now we're going to use that because we can get the enthalpy and the entropy at 6, because we know the pressure and temperature. Now the entropy at 7 is the same as at 6, so we have the pressure at 7. And so we have a quality factor, so we're actually in the two-phase region here at 7. We have a quality factor of about 92%, and then we can get the enthalpy at 7. And the entropy at 8 is the same as at 6, so we know the entropy and we know the pressure, so we can get the quality factor there. It's about 79%, and we can get the enthalpy there. Now, the work through in the first case, the work through so this is A. This is case A, where we basically, there's no flow here. So there's a valve here or something. We're shutting things off here, and we're taking everything out of here. So in that case, we have the mass flow rate, the full mass flow rate, and then the power output is the difference in enthalpy from 6 and 7. And that winds up being about 3.3 megawatts. We're getting out in the case where we're trying to get more heat out. So then the process heater, in this case, again, M7 now is also M6, because again, M8 is 0. And so in that case, we're getting a process heat out from the process heater. So we're getting heat out of about 9.7 megawatts of heat coming out of here. So that's the case where this is all shut off. All these blue things have 0 flow in them. And now in the other case, we have to look at this at the case where we have 60% coming here and then 40% coming out here. So in this case, we can see we get, this is the old work output of the turbine, and then we get this additional because now we have some of the flow continuing on through. And so we get some extra work out of the turbine. And so now we're up to about 4.25 megawatts. So by doing this, we're getting more work out of the turbine. But if we look at now, the M7 is now different than from here. It's only 3. It's only 60%. So we can figure out the process heater, the heat out of the process heater, in this case, is about 5.8 megawatts. So again, we've traded off. We've lost some heat from the process heater, but we've gained some work from the turbine by either shutting this off or opening it up.